So it's me again, and I just wanted to add a couple of things that perhaps weren't covered in the earlier videos. So first thing is what happens if you're asked to find a second derivative of an implicitly defined function. So in this case, we're being asked to find d squared y over dx squared, which is really just another way of writing y double prime, y prime prime, where the curve is 2x cubed minus 3y squared equals 8. So essentially what you do is it's really the same as finding a second derivative for a normally defined function. You just differentiate twice. It's just that there's a little bit of complexity in how you do this. So first let's go ahead and find find the derivative, the first derivative implicitly. So this is going to be the derivative of 2x cubed is 6x squared, and the derivative of 3y squared is going to be 6y, and since this is y, since we're finding dy over dx, this is going to be y prime. I could write it as dy dx, but I'm just going to write it in the shorter form, y prime. And of course the derivative of the constant is 0. So if I now solve for y prime, what I get is, I get here 6x squared equals 6y y prime, and I'll move that, sorry, I'm going to come down here. That gives us 6y y prime equals 6x squared. I can cancel the 6's, and I get y prime equals x squared, and then finally I get y prime equals x squared over y. So now that I have y prime, what I'm really being asked to do is to find y double prime. So let's do that. Sorry, I'm making a little bit of a mess of this page. Let's come over here and do that. Let's differentiate both sides of this equation. So first of all, on the left, what's the derivative of y prime? Well, we don't really know anything about it except the derivative of y prime is y prime prime, because that's what y prime prime is the derivative of y prime. And on the right side, we're just going to use the quotient rule. So we have y on the bottom and x squared on the top. So we have y times the derivative of x squared, which is 2x, minus the top, x squared, times the derivative of y, which is all we know about the derivative of y is that it's called y prime. And then on the bottom we have y squared. Okay, so that's the derivative of y prime prime. The only thing is, we already know what y prime is. We can replace it with an expression that just involves x's and y's without using any y prime, which you do in fact want to do. You want to write the second derivative of y just in terms of x's and y's. So let's just simplify this a bit, and let's see, y times 2x over y squared is just going to be 2x over y, and then subtract from that, I have x squared over x squared y prime over y squared, so that's x squared over y squared, the whole thing is times y prime, and now as a final step I'm going to replace y prime with x squared over y squared, so this now equals 2x over y minus x squared times x squared is x to the fourth over y times y squared is y cubed. So that's the answer. This is y prime prime, or d squared y over dx squared. So another type of issue that comes up just in our problem sets is to find dr over d theta for an implicitly defined function. This really is no different. It really doesn't make any difference what we call the variables. It's just that you have to keep in mind y, r, and theta have to be treated differently. But it's the same reason that y and x have to be treated differently when you're defining the function in terms of x and y. So in this case, note that if I wanted to find, if I had a normal function of x and y, like say x squared plus y squared equals 1, I'd be finding dy over dx. So x would be the one that I treat normally, and y is the one that I'd have to treat specially. So it's the same thing here. In this case, it's the bottom. It's theta that gets treated normally, and it's r that gets treated specially. So probably, though, I'm going to demonstrate a better way of thinking about that, however. So let's suppose that, let's rewrite this again. Theta squared plus r squared equals 1. So I want to differentiate this term, first of all. So first of all, think of this as kind of a composite function. Essentially, it's theta inside the squared function. So theta itself is the inside and squared is the outside. Well, we know how to handle that, because what we're going to do is we're going to write 2 theta and then times, that's just the power rule, and then times the derivative of the inside function, which was theta. So That's going to be the derivative of theta with respect to theta. How do I know the theta goes on the bottom? Because that's what I'm being asked to find. I'm being asked to find the derivative of this whole expression with respect to theta. So then here we're going to do the same thing with r. This is going to be 2r times the derivative of r with respect to theta. So, and then finally on the right we have the derivative of a constant is 0. Now, this expression means is equal to exactly what you think it is. If I had written dx over d, if I had written, let's say, d over dx of x, in other words, find the derivative of x with respect to itself, you would know that that's just 1. In other words, how fast does x change when x changes? And the answer is that it changes at a rate of 1. So this is, so here, this term is simply equal to 1. This term, we don't know anything about it except that it's dr d theta. And that's exactly what you would have expected if I had instead given you the problem x squared plus y squared. You would expect that there would be no derivative after the x, but there would be a derivative of y after the y. So this is just going to be 2 theta times 1, so I write nothing there, and then 2r dr d theta. In other words, the simplification of this, d over d theta r is just dr d theta. So that comes out to 0. We now just simplify, get 2r dr d theta equals negative 2 theta, and finally dr d theta equals negative 2 theta over 2r, which is equal to negative theta over r. And as you can see, the only reason this is in any way confusing is because I think many people sort of mechanically think with an x and y function, they say, oh, well, I'll just treat x like it's just, finding a normal derivative, and then with y, you put, I'm just going to multiply, whatever I get by y prime. That does work, but by changing the names of the variables, we force you to think about what the role of x and y is in this expression in dr and d theta, and realize that it's the bottom one that gets treated like x, that gets treated like, like it's just an ordinary derivative, and it's the variable on top that gets treated specially.